Hello everyone. In today's video, I'll be showing you on how to hybridize the molecule nitrogen trifluoride. So step one is for hybridization, you actually have to draw a Lewis dot diagram. If you're not familiar with the Lewis dot diagram, don't worry. It is quite simple and all you will need is your periodic table. So our molecule is again nitrogen trifluoride. So our two atoms will be nitrogen and fluorine. If we look at nitrogen first, we can see that it has a valence of 5 electrons. And the valence of fluorine is 7 because it is a halogen. And halogens have a valence of 7 electrons. So, now that we know the valence electrons of both our atoms, we need to draw the actual diagram. So, our central atom will be nitrogen because out of the two atoms, nitrogen has the lowest electronegativity. So go ahead and draw, I'll use a bigger Sharpie, nitrogen, and then you draw your surrounding atoms, which is trifluoride, or simply just 3 fluorines. So, immediately, we notice that none of these have a full octet. So we immediately draw single bonds. These will represent 2 electrons, and I'll show you. So, we will have to do our half calculation. Nitrogen has a valence of 5, and fluorine has a valence of 7. However, in this case, we have 3 fluorines, so we're going to have to multiply 7 by 3. If we do the calculation, 7 times 3 is 21, 5 plus 21 is 26. 26 electrons. Now, these represent 2 electrons. Now we just have to draw in the rest of the electrons for the surrounding atoms. So if this is 2, then we'll have to get 6 electrons around. So 2, 4, and 6. 2, 4, 6, and 8. That's one full complete octet. Now you just do the same for the rest. So 2, 4, 6, 2, 4, 6. And now our surrounding atoms are happy. They have 8 electrons. However, our nitrogen, on the other hand, is not so happy because it only has 2, 4, 6 electrons. It's still missing 2. So we will have a lone pair. Now, mathematically, we have, without these 6 electrons here, on our surrounding atoms we'll have 6 electrons. 6 times 3 is 18. 18 plus 2 plus 2 plus 2, which is 6. So 18 plus 6 would be 24. And as you can see, 26 minus 24 rather would give us 2 electrons. And that's what gave us this lone pair. So that is our Lewis dot diagram for nitrogen trifluoride. Now we move on to step 2, which is condensed electron configuration. So, in order to get the condensed electron configuration, we have to do, well, 2 things. First thing is we know that nitrogen has a total of 7 electrons, and we can see that in the periodic table. So we know we have to get a total of 7 electrons. However, this is the condensed electron configuration. So condensed means that we look at our atom, which is nitrogen, our central atom, and we go look to see what the previous noble gas is. In this case, it would be helium. So remember, it's the previous noble gas. It won't be neon because neon is in the same row. It will be the noble gas in the previous row. In this case, it will be helium. Helium has 2 electrons. So This here is the electron configuration chart. Now, we must note there are 4 different types of orbitals: S, P, D, and F. S orbitals have a max of 2 electrons. D orbitals have a max of 6 electrons. D has have max of 10 electrons, and F has a max of 14 electrons. So we have helium. We established that helium has 2 electrons, so we'll begin over here. 1s squared, or 1s2, which is, this is 2 electrons. This is our helium. So in this case, we would write helium. We wouldn't write the number. So we have helium. Now we move on. We go in the direction of the arrow. So it'll be 1s, then 2s, 2p6, 3s2, and so on. So next we'd go to 2s squared. We write 2s squared, and that's a total of 4 electrons. Now, this is the tricky part, and I see I did it here already. 2p6, we have a p orbital. P orbitals, again, have a max of 6 electrons. However, we do not need all 6 in this case. We already have 4. I already finished it, but we have 4 currently. This is where we are right now. 2 plus 2 is 4, plus 6 would give us 10. We need 7. We only need 3, so we would write 2p3 instead of 2p6. That's why I have the 6 crossed out and I put a 3. So we got this one, which is the helium. So we write helium, we don't write this. Then 2s squared, check, and then 2p3, check. So that is our condensed electron configuration of nitrogen. Now we move on to step 3. Step 3 is the condensed energy diagram. So we have 2 different types of orbitals in our configuration: s orbital and p orbitals. So we'd write it here, as you can see, types of orbitals, s and p. You divide the s and p with a dotted line, and this here just represents the energy going from lowest to highest. So to begin, we write helium, which is the beginning of our condensed. We write it here, followed by our s orbital, which is 2s, one line over it. Then we have 2p3. So we have 2p here, and we have 3 because it's 3. So there's 2 principles we have to follow here. We have to follow the off-bow principle, which is that we fill lowest orbitals are filled first, and then Hund's rule, where all orbitals are filled with a single electron before they're doubled. So in this case, it would be 1 here, 1, 1, and 1. Now we have to double this one here. So this would be doubled. This downwards arrow represents an electron. So now we have 2 electrons, 2, 3, 4, and 5. This would match our valence that we're looking for. Now, moving on, we have to move on to step number 4, which is hybridization. So this is the actual hybridization. Everything leading up to this point was just the preparation that we needed to do to reach this point. This is where we have to go back actually to our Lewis dot diagram. In our Lewis dot diagram, we have these 3 bonds here. These are called single bonds. That's what they're commonly referred to, but they are actually called sigma bonds. And we have 3 of them. So here's 1, 2, and 3. That's why we have 3 sigma. This is the symbol for sigma. 3 sigma bonds. And we also have 1 lone pair, which is sitting on our central atom, nitrogen. So we also circle that. So we have 4 things. So we have 4 things. So then you would draw 4 orbitals. 4. All right, so now we have our 4 orbitals drawn in. Now, following Hund's rule again, we will first fill each orbital with a single electron before we start pairing. So now we have a single electron in each, and now we will pair. So this would be 2, plus 1 is 3, plus 1 is 4, plus 1 is 5. So that matches our valence of nitrogen. So now we have 4 things. So we just do 4 check marks here. 1, 2, 3, and 4. And that's all our rough work. Now we're ready to write the hybridized configuration. So using our Sharpie, we will start with 2, the number 2. It'll be 2s. We have 1, so it'll just be s, p, and then 3. We have 3 p's, 3 check marks. So it'll be 2s, p, 3. And there you have it. That is the hybridized orbital or hybridized electron configuration of nitrogen. Now we're going to focus more on nitrogen. So, intramolecular forces present in the molecule itself. So for bonds, there are no special bonds. There's sigma bonds are present. However, there are polar covalent bonds. Now for this, going back to the special bonds, there are no coordinate covalent bonds or resonance structures. That's why we put no special bonds. However, there are polar covalent bonds. If you look at the electronegativity periodic table, if you go to nitrogen, it has electronegativity of 3, and fluorine has an electronegativity of 4. So if we were to take the highest electronegativity subtracted by the lower, you would get 1. 1 is between 0.4 and 1.7. So if we were to use this as a guide, our answer is 1. That's our electronegativity of the molecule. It'll be polar covalent because 1 is greater than 0.4 and it's less than 1.7. So it fits in here for a polar covalent bond. So that's our intramolecular forces. Now, for intermolecular forces, we have London dispersion forces. They are present in both nonpolar and polar molecules. And we have dipole-dipole. So, going back to our Lewis dot diagram, you can see we have a lone pair. What this lone pair will do is it will actually push the surrounding atoms downwards, creating 2 poles. So it will be the lone pair will be at the top, and the 3 fluorines would be pushed to the bottom to create a trigonal pyramidal. And that's how you'll get the dipole-dipole. And those are the 2 intermolecular forces that are present in our molecule. Now, for physical properties. So for the physical properties, the melting point of nitrogen trifluoride is negative 129 degrees Celsius, and the boiling point is negative 206 degrees Celsius. Nitrogen trifluoride is also a colorless gas, and it has a very strong musty odor. So that is it for how to hybridize the molecule nitrogen trifluoride. Thank you.